Swayam Prabha. Digital India. Educated India.
So in the second lecture on generating functions, we will see more applications. For example, in this counting compositions and partitions of positive integers. Also, at the end, I will introduce the concept of exponential generating functions. Okay, so let's start with the applications first. I start with a few recalling of concepts already introduced earlier. So, ordered and unordered partitions of positive integers. So, let n be a positive integer, natural number. Now, we ask the question, in how many ways I can write n as a sum of positive summands? Okay. In how many ways can n be written as a sum of positive integers? So, this is the basic question. And then, if I take into account or consider the different ways of arranging the summands, then we are talking about compositions, and if I ignore their order, rearrangements, I am talking about partitions. So, we have defined this earlier. The order of the summands is important. We are talking about compositions. If not important, then we are talking about partitions. Okay. For example, all compositions of 4 are 4, 1 plus 3, 3 plus 1, 2 plus 2, 1 plus 1 plus 2, 1 plus 2 plus 1, 1 plus 1 plus 2 and 1 plus 1 plus 1 plus 1. So, I am treating, for example, 1 plus 3 and 3 plus 1 as distinct. Okay. Also, 1 plus 1 plus 2, 1 plus 2 plus 1, 1 plus 1 plus 2. These are also considered distinct compositions. Okay. So, 1, 2, 3, 4, 5, 6, 7, 8. 8 compositions of 4. On the other hand, if I consider this and this as essentially the same sum, likewise this and this as the same sum, we are talking about unordered partitions, which are also simply called partitions. So, all partitions of 4 are therefore 4, 1 plus 3, 2 plus 2, 1 plus 1 plus 2 and 1 plus 1 plus 1 plus 1. So, how many are there? 1, 2, 3, 4, 5. So, 5 partitions, whereas 8 compositions for 4. Okay. So, earlier we have deduced a formula that the number of compositions of n is 2 power n minus 1. We will re-deduce the same formula, but this time using the theory of generating functions. Unfortunately, for partitions, that is unordered partitions, we can have some generating functions, but we do not know closed form formula. Okay. Anyway, we will still work with in the light of generating functions. We will once again deduce this and we will look at generating functions of partitions and some similar things. Okay, so first let us count compositions, ordered partitions. Okay, counting compositions. Now, what do I do? In order to count compositions of n, we have to see how many summands are there. Okay. If there is only one summand, okay, so classify compositions by the number of summands. If we have only one summand, then there is only one way of writing each n. For example, 1 can be written as 1, 2 can be written as 2, 3 can be written as 3, and so on. So the relevant generating function is this, x plus x square plus x cube and so on, x over 1 minus x. Okay, then if I consider two summands, it may be 1, 2, 3, another 1, 2, 3 whole square. So it's the coefficient of x power n in this, which simplifies to x over 1 minus x whole square. In general, if I consider I summands for some I greater than equal to 1, we consider the coefficient of x power n in x plus x square plus x cube and so on whole power I, that is x over 1 minus x whole power I. And these different cases for I are mutually exclusive. So one summand cases, two summand cases, three summand cases, these are all mutually exclusive. Therefore, the final generating function for the number of compositions of n is just the sum of all these things for different values of I. Okay. So, eventually I have this expression. Generating function for the number of compositions of n is therefore sum of all these cases. X over 1 minus x whole power I greater than equal to 1. Now if I take one x over 1 minus x common, we are getting a, I would say, familiar series. This is 1 plus this quantity square plus this quantity cube, and I can use that formula 1 over 1 minus this quantity. Okay, and this simplifies to x over 1 minus 2x. Okay, now if I expand this 1 over 1 minus 2x, this looks like this. X times this x times 1 plus 2x to square x square to cube x cube and so on. And now if I multiply this by x, this becomes this. X, 2 square, 2 cube and so on. Therefore, if I look at the coefficient of x power n, it is 2 power n minus 1. So I once again deduce the same formula that the number of compositions of n greater than equal to 1 is 2 power n minus 1. Good. So this is a mechanical way of doing things using the same formula. Another interesting application of this is the next. We are also talking about compositions of n, but those that are palindromic. Okay, what does it mean? Let us look at compositions of 4. 2 plus 2. If I read from left to right and if I read from right to left, they are same. Here also 1 plus 2 plus 1, 1 plus 2 plus 1, 1 plus 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1. Okay. So such compositions are called palindromic if they read the same forward and backward. Also let us take a look at compositions, palindromic compositions of 5. You see, these are all possibilities. 2 plus 1 plus 2, 1 plus 3 plus 1 and 1 plus 1 plus 1 plus 1 plus 1. Also this 4, singleton 4 is also a palindromic composition, singleton 5 is also a palindromic composition. So how many are there? For 4, 1, 2, 3, 4. For 5 also we have 1, 2, 3, 4. I will now deduce a closed form formula for palindromic compositions of all n. Before doing that, let us look at some properties. Okay. Since we are talking about palindromic compositions, if the number of summands is even, something like this, n has to be even, because this sum must be the same. Only I have written this in the reverse order. Okay. Therefore, if the number of summands is even, n must be even. Or if I make a contraposition, if n is odd, the number of summands must be odd. Right. The second observation is that if, okay, so but this is not an if and only if, because for example 4 may have 3 summands, 4 summands, 2 summands, 1 summand, but 5 can have only 1 or 3 or 5 summands. 4 summands impossible. Okay. Another important observation is that whatever is appearing at the center, okay, let's assume the case of odd summands, odd number of summands, like this, except perhaps this. Okay. Then, this is an important observation. If the number of summands is odd, like this case, then the middle summand must have the same parity as n. Why? Because if I forget this middle quantity, then whatever appears here and whatever appears here are essentially the same thing. So just written in reverse order. Okay. So the sum of this part and this part, this part and this part, they must be same. Okay. So same quantity plus same quantity. So this gives an even number. And if I subtract it from this n, this parity and this parity, this parity and this parity, they must be the same. Another crucial observation is that if I have an odd summand case, then if I look at this left half and if I consider any composition of this part, then I can simply write that composition in the reverse order after this center. And the same is true for this. This center has a sign plus 2, and there are 2 compositions of 2 and 1 plus 2. Sorry, no. Yeah, this one. Here the center has plus, here also the center has plus. The 2 compositions of 2 and 1 plus 1. And after this, I just write it in the reverse order. Okay. So this is an important observation. To the left of the center may be either something like this, a summand, or a plus symbol. The left of the center, I can take any arbitrary composition, but then to the right of the center, we write just the same composition in the reverse order. Okay. This gives us these 3 observations, 3 or 4 observations. Let us deduce explicit formulas for the count of palindromic compositions of n. Okay. So as you see, this introduces an inherent asymmetry between even numbers and odd numbers. So I have to consider these 2 cases separately. Let us first look at case of odd numbers. So in that case, we know that the number of summands must be odd. Okay. So it can be n itself. So that is just one case. Okay. If we consider multiple summands, then we have already seen that the number of summands must be odd. Okay. Then also we have seen that whatever is sitting at the center, this is now a summand it must have the same parity as n, that is, it must be odd. Okay. So the central summand must be odd. Odd means it can be any one of 1, 3, 5, 7 up to n minus 2. The case n I have already considered separately. Okay. Now, if 1 sits at the center, the total sum come from the two sides of this will be n minus 1, and that will be equally distributed to the two sides. If the central summand is 7, n minus 7 is the total sum coming from the two sides, and they are equally distributed to the two sides. Okay. So, the remaining sum, that is n minus 1 or n minus 3 or n minus 5 or 2, is equally distributed to the two sides of the center. Okay. So, what should be the numbers then? N minus 1 by 2 or n minus 3 by 2 or n minus 5 by 2 or n minus 7 by 2 or 1. Or if I count from this direction, 1, 2, 3, 4 up to n minus 1 by 2. Okay. And then I have already explained that if I fix any composition in either side, maybe to the left side, the other one is also fixed. Okay. So the total number of cases in this case is this one, single case, plus 2 power n minus 1 by 2 minus 1, 2 power n minus 3 by 2 minus 1, and so on. And this simplifies to 2 power n minus 1 by 2. If n is odd, this is same as the floor of n over 2. So this is the case for the number of palindromic compositions in the case n is odd. Now let us look at the case of n being even. Now recall that n may have, okay, first case is obviously there is only one summand which is n, so one case. So now consider n having written as a sum of multiple positive integers, multiple summands, 2 or more. Okay. Now recall that if n is even, there are two possibilities. The number of summands can be even and the number of summands can be odd. Okay. So let us first handle the case that the number of summands is odd, because this is similar to the previous case. Okay. Then we have also argued that the central summand must be even, same parity as n, therefore central summand must be even. Okay. So that means it must be of the form 2, 4, 6, 8 up to n minus 2. Okay. And then the remaining sum is n minus 2, n minus 4, n minus 6, n minus 8 up to 2. That has to be equally distributed to the two sides. Okay. Remaining sum can be this, and it could distributed equally to the two sides. And therefore, using the same formula, the total number of palindromic compositions, including this case an odd number of summands, this becomes, this is 1 for this case, and then this by 2 minus 1, 2 power n minus 4 by 2 minus 1, 2 power n by 6 by 2 minus 1. This simplifies to 2 power n minus 2 by 2. This minus 1 and then plus 1 actually cancels. This is 2 power n by 2 minus 1. Now finally I consider the case that n consists of even number of summands. Okay. A sum consists of an even number of summands. Okay. If the number of summands is even, then what happens? A plus sign is sitting at the center. Therefore, to the left I will have n by 2, to the right of that plus I will have n by 2. That is, any composition of n by 2 gives a palindromic composition of n. And in this case, the count is 2 power n by 2 minus 1. Now, if I add these two counts up, I see that total count is 2 power n by 2. Since n is even, this n by 2 is also the same as the floor of n by 2. So this is the unifying formula, 2 to the power floor of n by 2, that holds in both the cases when n is even and n is odd. Okay. So we can derive a lot of things about compositions, but partitions are bit more complicated. Let us now look at partitions. So we denote by P of n the number of partitions of n. Okay. And I want to find some handle on this P of n. Okay. Now, definitely, since order is not important, I need to count how many times each I in n may occur in this sum. Okay. So, I just say 1 appears 2 times, 2 appears never, 3 appears 5 times. That uniquely defines the sum. Okay. But then 2 times 1 plus 0 times 2 plus 5 times 3 plus whatever, sum must be equal to n. Okay. So, let us look at each I, this case of each I. So, 1 may occur never, or once, or twice, or thrice, or 4 times, and so on. And this leads to the power series 1 plus x square plus x cube and so on. And this is familiar thing, 1 over 1 minus x. 2 may occur similarly, never, or once, or twice, or thrice. But 2 will contribute 2, x square, x power 4, x power 6, something like that. So, 2 may occur never, or once, or twice, or thrice, or so on. And this leads to this power series 1 plus x square plus x power 4 plus x power 6 plus x power 8 and so on. And this simplifies to 1 over 1 minus x square. In general, any I may occur never, or once, or twice, or thrice and so on. And this gives this power series 1 plus x power I plus x power 2i plus x power 3i and so on. And once again, this is a familiar thing, 1 over 1 minus x power I. Now to sum up, you have to multiply all the things, okay, for all values of I. Okay. Whenever you are considering partitions of n, okay, so in order to get this desired generating function, okay, so you multiply all these things for I greater than or equal to 1. But this is an infinite product, it's not a very good thing, and it's difficult to simplify this any further. Of course, if you are interested in the partitions of n, we do not require these factors for I greater than n. Despite that, the formula does not simplify much to give us something like a closed form expression of P of n. So, this does not help actually. We still do not get any closed form formula for P of n. But at least we can see that this is the generating function of P of n. That's not, I would say, a bad achievement. Okay, we do not have any, at least I can use this for counting P of n for given values of n, like 100 maybe. Okay. Okay, so that's not too bad. Now, I consider two different types of partitions. For them also I do not have explicit formulas, but their generating functions are interesting. First, let us count the partitions of n with distinct summands. Okay, so here is an example. Okay, so PD of n is the number of partitions of n in which all the summands are distinct. Okay. So, for example, if I consider 7, these are only possibilities. 7 itself 1 plus 6, 2 plus 5, 3 plus 4 and 1 plus 2 plus 4. Therefore, P distinct 7 is 5. Okay. And now I want to find the generating function of this series PDN. So now note that each I may occur once or never. Okay, it cannot be repeated. So each I in N can occur either 0 time or 1 time in the sum. Therefore, the relevant series for any I is 1 plus x power I. Other terms will not be present. And the generating function of this will be the product of all these things. Okay. Generating function of PDN is 1 plus x, 1 plus x square, 1 plus x cube and so on. All I greater than equal to 1, 1 plus x power I. This is still an infinite thing and I can truncate it at I equal to n. After I equal to n, this still does not give us any explicit formula. Then I look at a third example of partitions where I consider only odd summands. 1, 3, 5, 7, 9. Only these things can appear as summands. Okay. And now let us see. Let us give this name PO of n is the number of partition of n with odd summands. For example, 7 can be written as 7, 1 plus 1 plus 5. This is repeated, but all summands are odd. 1 plus 3 plus 3, 1 plus 1 plus 1 plus 1 plus 3 and 7 ones. So 1, 2, 3, 4, 5. Okay. So PO7 is 5. Like PD7 equal to 5, PO7 is also equal to 5. We will soon see that this is no coincidence. This is the rule actually. Anyway, I'll come to that. But let me first find a generating function for this PON. Now, of course, only 1, 3, 5 and 5, 7, 9, the odd numbers are allowed in the sum. Therefore, this is the relevant thing. 1 plus, this is for 1, x square, x cube. This is for 3, x cube, x power 6, x power 9, 5, 10, 15 and so on. This is once again this infinite product. 1, 1 minus x, 1 minus x cube, 1 over 1 minus x power 5 and so on. And I can write it this way. 1 over 1 minus x to the power 2i minus 1 for all I greater than equal to 1. Okay. This is still not a good thing from which I can derive a closed form expression for this quantity. Anyway, we have to accept reality. So now, let us look at this thing that PD7 is 5, PO7 is also 5. In fact, we will show that this generating function and this generating function are essentially the same. And therefore, they will generate the same sequence. In particular, PD of n will be equal to PO of n for all values of n. Okay, so why are these two apparently different looking generating functions are the same? For that, I will write this 1 plus x power I as 1 minus x power 2i over 1 minus x power I. And then doing a little bit of maths, cancellation from numerator and denominator, will simply lead us to this formula. Let us see how this happens. Equality of the last two generating functions. So I simply write 1 plus x power I as 1 minus x power 2i over 1 minus x power I. Then this product becomes this is the product for all I greater than equal to 1. This is the same. Now, let me write this term by term. For I equal to 1, this is x square, 1 over 1 minus x power 4, 1 minus x square. For 3, 1 minus x power 6, 1 minus x power 8. For 4, 1 minus x power 8 over 1 minus x power 4. Now you see that this and this cancel. This and this cancel. This and this will cancel somewhere in future. This and this will cancel somewhere in future. So what are the things that still remain? These are nothing but x, x cube, x power 5, these things. Okay. But that is nothing but the generating function of PON. This is the generating function of PDN. This is the generating function of PON. Since they are same, it follows that PDN is equal to PON for all n in n. Okay. So that's nice. Now, since we do not have closed form expressions for partitions, people have devised several tools for understanding partitions and proving several properties of them. So one such tool is called Ferrers diagram or Ferrers graph. I am not very much in favor of calling this Ferrers graphs, because in computer science graphs are used to denote something, but since these are diagrams anyway, so we can call Ferrers diagrams. So this picture shows two I would say partitions of 20. This is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 1, 2. So 20 is equal to 7 plus 5 plus 4 plus 2 plus 2. So this Ferrers diagram or Ferrers diagram shows us a partition of 20. Okay. So this Ferrers diagram also shows us a partition of 20. This is 5 plus 5 plus 3 plus 3 plus 2 plus 1 plus 1. Okay. So this diagram shows this partition. This diagram shows this partition. Now if I carefully look at these two, we see that I have generated this from this by simply transposing the rows and the columns. This row has become this column. This row has become this column. This row has become this column. This row, this column, this row, this column. Okay. Now, from this pictorial representation, I can conclude that the number of partitions of n into m Summands, in this case partitions of 20 into 5 Summands, is equal to the number of partitions of n into Summands, some number of Summands, but among these Summands, m will be the largest. So this is 1, 2, 3, 4, 5, and in the transposition, 5 is the largest Summand. Likewise, if I look at this, 1, 2, 3, 4, 5, 6, 7 Summands, so its transposition, which is once again back to this thing, here the largest Summand is 7. Okay. So these are interesting results. In absence of closed form formulas, we often play with such interesting results. This is a pictorial thing. And I give you an exercise related to this. You can use this using Ferrers diagram. Prove that the number of partitions of n is equal to the number of partitions of 2n into n Summands. Okay, not a difficult thing, but I am leaving this to you as an exercise. Okay. Fine. So, That's all about generating functions and their applications. I now introduce a new type of generating functions called exponential generating functions. So far, we are mostly interested in combinations. These exponential generating functions have something to do with permutations. Why? To motivate you, let us look at the binomial expansion of 1 plus x power n. So I am writing it in this form. This is actually n choose 0, n choose 1, but I am writing this way. Cn0 plus Cn1x, Cn, 2x square and so on. So this is the generating function of Cn0, Cn1, Cn2, Cn, and then this is followed by 0, 0, 0, 0, 0. If I now write this expansion in terms of the permutation coefficients Pni, then this will look like this. Pn0 over factorial 0, Pn1 over 1 factorial x, Pn2 2 factorial over 2 factorial x square, Pni I factorial x power I, and so on. Okay. So, this leads us to the following concept. Now consider, instead of these very specific sequences, let's say a0, a1, a2, an be an infinite sequence of real numbers, maybe complex numbers, not a problem. The ordinary generating function of the sequence is nothing but a0 plus a1x plus a2x square and so on. We have defined this quantity as the generating function of this sequence. Now, since another type of generating functions is in the scene now, I want to highlight that this is the ordinary generating function. However, we may make the convention that if we simply say generating function, we always imply ordinary generating function. Anyway, so what about this new concept? Okay, the new concept is exponential generating function. The same thing, only thing is that 0 factorial, 1 factorial, 2 factorial, this will now appear in the denominator. Okay, so the exponential generating function is a0 over 0 factorial plus a1 over 1 factorial times x, a2 over 2 factorial times x square and so on. Okay, and now as I mentioned, as this tends to motivate us, these exponential generating functions are used for counting permutations or arrangements. Okay, whereas these ordinary generating functions are typically used for counting combinations. Okay. Anyway, let us look at a few examples and applications of these exponential generating functions before I stop today. Some simple examples. We know that e to the power x is 1 plus x square by 2 factorial and so on. So this is the exponential generating function of 1, 1, 1, 1, 1, the constant sequence 1. Also, this is the ordinary generating function of 1. Actually, over 0 factorial is not written here. Likewise, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, and so on. Okay, so that's a simple example. Another example could be this: e power x plus e power minus x by 2. This is, I think, cos hyperbolic x. So this x cube, these terms will cancel. So we will have something 1 plus x square by 2 factorial, x power 4 by 4 factorial, and so on. This is the exponential generating function of 1, 0, 1, 0, 1, 0, and so on. Likewise, if I consider the sine hyperbolic function, e to the power x minus e to the power x minus e to the power minus x by 2, only odd terms will be there. X cubed by 3 factorial, x 5 by 5 factorial. This is the exponential generating function of 0, 1 is not there, 0, 1, 0, 1, 0, 1, 0, 1, and so on. Okay, so these are simple examples. Let us look at a couple of applications of exponential generating functions. The first application shows that there is a strong connection of exponential generating functions with permutations. Okay, so we will solve this counting problem. How many arrangements of 4 letters are possible if these letters are taken from this set, ananas? Okay, so I am not considering how many, 1, 2, 3, 4, 5, 6 letters are there. I am not talking about the arrangements of all these 6 letters, but only 4 letters I will take from this. Okay, and I am asking how many arrangements are possible. Okay, so now let us count this A, N and S. See that there are 3 A's, 2 N's and 1 S. Therefore, A can appear 0 times, 1 time or once or twice or thrice. Cannot be more than that because there are only 3 A's. 2 N's, so N can appear 0 times or once or twice. S, it can appear either 0 time or once. So the exponential generating function of all arrangements is this. This is for A, this is for N, and this is for S. Okay. 0, 1, 2 or 3, 0, 1 or 2, this is for N, for S, this is either 0 or 1. Okay. And I am interested in 4 letter arrangements. So I need to look at the coefficient of x power 4. Actually, I will not look at the coefficient of x power 4. I will look at the coefficient of x power 4 over 4 factorial. Okay, that's how this works. Anyway, if I look at the term that consists of x power 4, let us see. The term involving x power 4 is, I may take this and this. This will give me one term involving x power 4. Okay. This implies 3 A's are chosen. This is N, 1 N is chosen, no S is chosen because this is 1. Other possibilities, this and this. This and this. So this corresponds to 3 choices of A, 1 choice, no choice of N, 1 S to take. Then I look at this, 2, 2, 1. Okay, this. That is, you take 2 A's, 2 N's and no S. This gives you this term, this, A, N, N. You can also choose this and this. That is 2A, 1N, 1S. This will give you this. Finally, there is a last possibility, this and this. That is 1A, 2N, 1S. 1A, 2N, 1S. So this. Okay. So this will give me all the x power 4 thing in the final product, and I am interested in not the coefficient of x power 4 but the coefficient of x power 4 over 4 factorial. That will be 4 factorial by 3 factorial, 4 factorial by 3 factorial, 4 factorial by 2 factorial times 2 factorial, 4 factorial by 2 factorial, 4 factorial by 2 factorial. That is precisely this first thing, the number of permutations of AAN. This is precisely the number of permutations of AAS. This is precisely the number of permutations of AANN. Here AA, 1N, 1S. Here also 1A, NN and S. Okay. So, this example illustrates that exponential generating functions are essentially related to counting permutations or arrangements. Okay. Fine. Okay. Fine. So this is our first application. As a second application, I show once again an arrangement counting problem. So this is second application. So the question is, how many strings of length n greater than 0? That is the reason why I am not considering n equal to 0 are there over the 4-letter alphabet A, B, C, D, such that the following two conditions hold. Okay. The number of C's is odd and the number of D's is even. A's and B's may occur any number of times, odd or even, no restrictions. For C it is odd, for D it is even. Now, a string is an ordered quantity. So if you say your string contains 5 A's, 6 B's, 3 C's and 8 D's, it does not specify the string. You have to precisely say where these 5 A's, 3 B's or whatever I told, 6 B's, 3 C's and 8 D's they occur. Okay. Therefore, this is essentially I am talking about the arrangement of n symbols coming from ABCD with the restriction that the number of C's is odd and number of D's is even. No restriction on number of A's and number of B's. Okay. So, since this is the case, the exponential generating function is 1 plus x square over 2 cube plus x cube over 3 factorial, x square over 2 factorial plus x cube over 3 factorial and so on. This pertains to A and B, so two things, so square. For C, the number must be odd. So 2, 0, 4, these are not allowed. So we should consider only x plus x cubed by 3 factorial plus x power 5 by 5 factorial and so on. Finally, the number of D's must be even. Therefore, I will consider 0 D's or 2 D's or 4 D's or 6 D's and so on. And if I multiply this, this will be now the exponential generating function of the number of strings of length n satisfying these two conditions. Okay. Let us do this. It's simple algebraic manipulation now. So this is nothing but e power x whole square. This is nothing but sine hyperbolic x. This is nothing but cos hyperbolic x. Okay. And we know their explicit formulas. E to the power x whole square, e to the power 2x. This is e to the power x minus e to the power minus x over 2. This is e to the power x plus e to the power minus x over 2. Let us now do some little bit of playing with this. This is 1/4 times e to the power 2x. E to the power 2x minus e to the power minus 2x, fairly straightforward. Now I introduce this inside this. This gives me 1 over 4 e to the power 4x minus 1. And if I now expand this e to the power 4x, this will look like 1 over 4, 4x whole power n factorial. But the first term will vanish, 1 minus 1. So this is valid for n greater than or equal to 1. Okay. So now if I look at the coefficient of x power n over n factorial, this number will be 1 over 4 times n. Okay. So the coefficient of x power n over n factorial is 4 power n minus 1. And this is precisely the number of these strings. Okay. Okay, it may be good and interesting exercise to enumerate all strings of length 1, 2, 3 and see that this count is exactly coming. Maybe I will do it for n is 1. If n is 1, this condition 1 implies that only possible string is C. Okay. N is 2. C must appear once. Okay. C must appear once. D cannot appear because D's possibilities for D are 0, 2, 4. 2 is too large. 0 has to be the case. A and B may appear. So that means I may now have AC, BC, CA and CB. These are the 4 possibilities. Okay, so maybe you may look at this 16 possibilities for n equal to 3. Okay, work this out. Anyway, so these are some of the applications of exponential generating function. So for the moment I am going to stop. In the last hour on the treatise of generating functions, we will look at perhaps the most important application of generating functions, namely the use of generating functions for solving recurrence relations. Okay. In the next chapter, you will see mechanical procedures for solving the so-called linear recurrences, but we will give you a justification why these mechanical procedures work like that. Moreover, we will also solve a non-linear recurrence relation that cannot be solved using those mechanical procedures. So we need to use some powerful tools like generating functions. Anyway, we will see this in the next lecture. Until then, goodbye.